Let's see if we can determine the convergence of this infinite series n times 3 to the n divided by 5n cubed plus 1. Now this one's a mess. I mean, there's all sorts of terms. It clearly doesn't immediately look like any of our well-known types of series. So let's go through our list here and start ruling out some of the tests that would clearly not work. Some I see just right off the bat. This guy looks nothing like a P-series. Let's see, nothing like a geometric series. I would not have a clue how to integrate that guy. So if this was a continuous function, root test, I don't see powers of n going on. The direct comparison test is always a tough one because you have to be so careful with how your inequalities are going to work out when you make terms larger, smaller, looking for somebody to compare it to. Nth term test, maybe a possibility, but I could take this guy's limit as n goes to infinity. But even if the terms did go to 0, I would not be able to say if it converged. I would have to go to another test. My only hope was that the terms don't go to 0. So I think I might even hold off on that one. Ratio test is always a good option. Limit comparison test. If I can think of somebody that's a more stripped down version of this guy, the limit comparison test might be a good option. So we could run with either of the last two. For this one though, I think I'm going to choose the limit comparison test. It's a good rule of thumb. If you see somebody who looks just absolutely horrendous, consider him as your a sub n and try to compare him to somebody that's a lot simpler. So what do I mean by simpler? Let's see. If we did not consider the plus 1, I don't think the plus 1 is going to make a huge difference in convergence or divergence of this infinite series. If we drop that, this 5 isn't going to affect the convergence either. I'm basically looking at n times 3 to the n divided by n cubed. Those are the important terms. And even those would simplify. That would give us 3 to the n divided by n squared. Now, where the n squared come from? Roughly n over n cubed, right? So what you're doing is you're just looking for somebody to compare him to who's much simpler that we can determine some information about. So let's go with the limit comparison test, comparing him to b sub n, which is 3 to the n over n squared. All right, so we know how the limit comparison test works. We're going to take the limit as n approaches infinity of a sub n times 3 to the n divided by 5n cubed plus 1, a sub n divided by b sub n. B sub n was 3 to the n over n squared. Now, rarely is this what we actually do because normally these have fractions, and so fractions divided by fractions would actually best be written as multiplied by the reciprocal. That would be a lot easier way of putting it. So let's write instead times n squared over 3 to the n. Right? So hopefully you saw what we did there. We multiplied by a reciprocal instead of dividing by another fraction. All right, now, fortunately, I see a lot of good things. A lot of things cancel. The 3 to the n's would cancel. And you would roughly have limit as n approaches infinity, n cubed divided by 5n cubed plus 1. Now, these powers are the same. So you could use L'Hopital's rule if you wanted to write out all the details, but I think it's going to be pretty clear to most everybody that this limit at the end of the day will be 1/5 because these powers agree with one another, the highest powers. So this would be 1/5 if you would allow me just to kind of speed things along a little bit. All right, so now 1/5, what does that mean? Does that mean that the sum is 1/5? No, that's not what this means. The limit comparison test says that if this limit is finite and positive, which it is, finite and positive, then that means that this sum of the ugly series versus this summation, n equals 1 to infinity, of this slightly nicer compared series, 3 to the n over n squared. These will either converge together as a pair or diverge together as a pair. This is what this means when this number is finite and positive. All right, so really that means now all we have to do is focus our attention on the simpler series, and then whatever he turns out to be, that will also be the case for the original uglier series. Well, I think I see what's happening with this guy. This guy's going to diverge. He will diverge, and I'll write out the details in a second. This guy diverges by the nth term test. These terms don't go to 0. These terms get larger, not smaller. So since these diverge, then that means that this guy will diverge as well. Sorry, I'm kind of running out of room. This guy diverges by the limit comparison test. Now, I haven't really shown you that this diverges. It's a bit intuitive. I mean, you can see these terms are getting smaller. If you wanted to formally show it, then what you would need to do is take the limit as n goes to infinity for 3 to the n over n squared, and I mean, you can work out this algebra yourself, but I mean, you can just trust me, this is going to go to infinity, indicating that this series will diverge. Now, how can you see this goes to infinity? Well, as n goes to infinity, 3 to the n goes to infinity, and so does n squared. But if you keep taking L'Hopital's rule, the denominator will go from n squared to 2n when you take its derivative, and 2n will go to 2, right? So it gets smaller. Exponential derivatives keep looking like exponential terms again and again and again. So 3 to the n's derivative will have a 3 to the n, and his second and his third and his fourth derivative, they'll all have 3 to the n. So because he's not getting smaller, but he is, you can see that this limit will go to infinity. You probably want to write out some more details on your paper, but I'm just kind of giving you the short version of that. So he diverges by the nth term test. These guys are handcuffed together by the limit comparison test, since this ratio was finite and positive. And so since he diverged, so does our original series by the limit comparison test.